It's really great to be here. It's always great to be in Santa Barbara and the KITP. My thanks to the organizers for the kind invitation to speak about what's surely my favorite topic. Why are random quantum circuits capable of solving hard problems? This is going to be sort of a survey talk. I'm going to talk about a lot of papers over the last few years, but the latest paper is actually quite recent. So it just appeared in the last few months, and that's joint work with my collaborators, Adam Boland, Sean Dada, and Felipe Hernandez. So the starting point for this talk is maybe a deceptively simple question, which is, what does computation even mean? As I'm standing here, I'm realizing that it's a little embarrassing as a computer scientist that I don't really know the answer to this question. But I think maybe another perspective on this is that I think, a big part of computer science as a field is trying to understand what this means. So it's something we as a community has been thinking about for a long time. And, for the last 100 years, the de facto answer has been the so-called Church-Turing thesis, which says, that the Turing machine, a theoretical model of computation, is the universal model. So in other words, that any problem that can be solved by any feasible model of computation can be solved on a Turing machine. And now this is not, incredibly rigorous. What does a feasible model mean, for example, right? Well, it doesn't say that. But, after almost a century since this was first proposed, this is still well believed, and it hasn't really been threatened in a major way. But on the other hand, as computers get larger and the problems that they solve get more complicated, it becomes clear that we should talk about the speed of computation, that we should be talking about efficiency, right? And so, this Church-Turing thesis is extended in a way that neither Church nor Turing would have ever proposed, I think. But nonetheless, it's extended to say that the Turing machine is not only the universal model of computation, it's the universal model of efficient computation. So in other words, that the Turing machine is not much slower than any other model of feasible computation that will ever exist. And, I think these days, because efficiency is so important in everything that we do in society, I think this, maybe more than the original Church-Turing thesis, really is the foundation of modern computer science. It's really the starting point for everything that we do in computer science. And so I think that's why it's, absolutely astounding that the modern view is that this extended Church-Turing thesis, the one that's talking about efficiency, is probably false. And it's false for a really interesting reason, which is that, the Turing machine, as useful as it's been, fundamentally is ignoring how physics works. It's ignoring quantum mechanics. But this is not obvious, of course. The first evidence came, from Peter Shor, who was building on a lot of past work, who proved that, of course, quantum computers can, in theory, efficiently solve the integer factorization problem. Now, this is, a very pragmatic result. It means we're going to have to rethink all of our cryptography online. But I think, from my perspective, maybe even more interestingly, is just the conceptual message that Shor is saying. I think what Shor is saying here is, that understanding the power of efficient computation, which is arguably the goal of computer science, is inextricably linked to our understanding of physics. In other words, even if we're a computer scientist and we don't know much about physics, or for whatever reason we don't like physics, now this is sort of forced. It's, what Shor is saying is if we don't understand how physics works, we will be fundamentally missing how computer science works, right? So I've always found this sort of the most compelling message of, the most interesting message behind Shor's algorithm, but, there's this giant flashing caveat, right? Which is that, such idealized, large-scale, sort of fault-tolerant computers that can, factor a large number and break a cryptosystem or something, they didn't exist in Shor's day, they don't exist today. I think we've made a lot of progress, but I think if we're honest with ourselves, we're probably several years out. And so, this brings us to what I'm going to call quantum advantage. Some people call this quantum supremacy. For the sake of this talk, I'm going to call it quantum advantage. What I mean by this is the first experimental implementation of a provable quantum computational speedup implemented at a large scale, okay? Now, I think we're living in this extremely exciting era in which we've now seen the first claims of quantum advantage by experimental groups around the world. The first was, notably by Google in late 2019. They implemented the so-called random quantum circuit sampling proposal for quantum advantage using 53 superconducting qubits. This made the front page of the New York Times. The president tweeted about it. for whatever that's worth. Anyway, more recently, there's the so-called Gaussian boson sampling proposal for quantum advantage in a linear optical or photonics-based architecture. This has been implemented many times by the University of Science and Technology in China and by Xanadu, a Canadian startup company. And then in the last, say, year and a half, 2 years alone, there have been at least 3 subsequent experiments by Quantinuum using trapped ions, a updated superconducting experiment by Google, and then most recently, by which I mean literally like in the last 2 weeks, an updated Gaussian boson sampling experiment by USTC. So, if I'm looking at this, it seems pretty impressive. Like, surely we're sort of, pulling away from the line of classical simulability, and these experiments are getting better and better. But in fact, I think the reality is a bit more nuanced, right? So in fact, a lot of these experiments have now been simulated classically in a surprisingly short amount of time. So if we look, for example, at the original Google experiment, the number that the New York Times reported that was claimed in the Nature article for the random circuit sampling experiment was that the best classical simulation algorithm, would take 10,000 years to do the same thing that the quantum experiment just did, this random circuit experiment. But when people thought a lot more deeply about how these experiments worked, they were able to come up with, much more sophisticated classical algorithms that did the same thing in just over 14 seconds. Okay. Now, if we look at the second class of experiments, this is this USTC and Xanadu photonics-based Gaussian boson sampling experiment. Not wanting to be one-upped by Google, the original estimate for how long the best classical computer would take to simulate the experiment was 3.1 times 10 to the 10 years. That is a truly mind-boggling number, right? But in fact, I'm quite proud to say that when my group started to think about this experiment, and particularly, tried to understand the impact of the realistic rates of photon loss, which is the sort of dominant noise model of these types of experiments, these photonics-based experiments, we were able to come up with a totally different classical algorithm, nothing like what they were using to quote these 3.1 times 10 to the 10 numbers. This algorithm was designed to exploit these effects of the photon loss, right? It turned out their experiment had a lot less entanglement than they thought it was, and we were able to use that to simulate their experiment in less than 1 hour on a classical supercomputer at Argonne National Labs, which is pretty close to the campus of UChicago. So now you're sort of looking at this, and it's almost embarrassing. It's like maybe these experimentalists had absolutely no clue how hard it was to simulate their experiment, right? But I would argue that although there's some truth to that, the real truth is even more nuanced, right? If you look at these most recent experiments, right, there's sort of been a feedback loop where, the experimentalists learn from, the prior generation and the algorithms that have simulated them, and, they then respond, and they create, generally speaking, less noisy and at the same time larger systems. And so, in fact, if we look at these 3, the Quantinuum experiment, the latest Google experiment, and the USTC experiment that came out 2 weeks ago, the numbers keep coming. The latest claim is that, by Google, it should take something like 10 to the 25 years to simulate their experiment. Judging by the past history, I have to say I'm a bit skeptical of these claims, but I also want to say that I don't know how to contradict this, right? They have, of course, done their homework. They are quoting the best-known classical algorithms, and it is consistent with anything I'm about to tell you that, in fact, this is the real answer. Okay? That slide is a little bit controversial, so let me just stop for questions before I go on. So, any questions about this? Yeah, please.
So, these different generations of experiments,
Yeah.
the experiments haven't changed much, but qubit number.
No, actually no. That's not quite true. It depends on the case. I would say the most important thing by far is the fidelity, right? So in fact, the lesson that we keep learning is that it's not enough to keep making the system size larger and larger and larger if we're not also decreasing the gate fidelities, or to keep the overall fidelity, reasonable, right? And in fact, that's exactly the issue that happened with this USTC experiment. That in fact, before they knew about our algorithm, the prior two generation of experiments, what happened is, between like 2021, 2022, the experiment got larger but also more noisy, right? And from our perspective of our classical algorithm, it actually meant that the newer algorithm was easier. And so in the most recent generation of experiments, they actually made the system size a little bit bigger, but it was mostly about reducing the rates of photon loss. I don't know if that answers the question, but it's a trade-off between a number of different factors. But I would say the most important thing is fidelity, not system size.
Okay, so that answers the question that if I take that 14.22 seconds algorithm from back in the day and would scale it up to
Right, exactly, precisely.
Right.
Right, but of course it doesn't say. I think what you mean. It doesn't say that no algorithm will ever be able to simulate this, and we're looking for that algorithm, of course, right? Yeah, please. Generally speaking, there's some component of tensor network, but the particular tensor network and the way that they work is all a little bit different. Yeah, I'm not sure I want to say more at the moment, but I wouldn't say they're all the same algorithm. Definitely not. Like, for example, our work, this Nature Physics paper, like that uses tensor networks, sort of as some subroutine somewhere. But what was really difficult is getting some sort of, realizing that in fact there was not much entanglement in these systems, so that the tensor network would work very well. Yeah. Sorry, any others before I go on? It's probably the most controversial part of the talk, so I'm happy to keep going. All right, so let's talk more about the math of what's going on. So what is random circuit sampling? Well, first of all of these experiments are solving variants of this problem. I'm going to describe the one that sort of roughly captures what Google is doing, but it's important to realize that all of these variants are doing something similar. So, what Google does, roughly speaking, is they generate a quantum circuit C on n qubits on a 2D lattice with D, which is some parameter. Let's think of it as like square root n or something like this, n is the number of qubits. So D layers of Har-random nearest neighbor gates. Each layer of gates might look something like this. The circles here in my diagram are qubits. The edges are Har-random 2-qubit nearest neighbor gates. This could be the first layer of gates. The second layer might look different. For example, we might imagine horizontal neighbors connected with a gate rather than vertical neighbors. But the point is, we start in the all zeros input state, something easy to prepare. We apply our random circuit, which consists of square root n different layers of gates, and then we measure all qubits in the computational basis. At the end of the day, we get a sample from a distribution I'll call D sub c over n-bit strings. That is the problem. Sampling from this distribution. It is something that a noiseless quantum computer does trivially, and what we're trying to say is that it's a hard problem. Any questions? Okay, great. So the interesting question, I think, is completely non-obvious, is why is a random quantum circuit hard for a classical computer? Why should sampling from this distribution that's generated by a random quantum circuit be so difficult for a classical computer? So the starting point for our investigation of this, which goes all the way back to 2019, is the following, I think, really intuitive fact, which is that there exists a very special, I'll call it a worst-case circuit, that's sort of that's known to be hard for classical algorithms. The intuition here is really clear. Let C be like the circuit behind Shor's algorithm, or something like that. Some very, very special circuit. Well, we don't expect C to be easy to simulate, or else we'd be able to solve the factoring problem, right? But also, if we're going to choose our gates randomly, we're incredibly unlikely to just stumble upon Shor's algorithm, right? But maybe counterintuitively, our main result is what we call worst to average case reduction for random circuit sampling. We think of this as sort of working in the context of a proof by contradiction. In other words, let's assume for contradiction that there was a classical algorithm that can efficiently simulate a random quantum circuit with probability 2/3, let's say, over the circuit. And what we do is we show how to use this algorithm to simulate the worst case circuit, okay? But we've been assuming that C is hard, that we can't simulate it efficiently, and therefore there can't be such an algorithm that simulates a random quantum circuit. So that is the logic. Of course, I'll tell you how this reduction works in a moment, but that's the logic. It works in the context of a proof by contradiction. Now, the one thing I want to say is that there's a technicality here, and by that I mean it's technical, but it's certainly very important, which is that when I say simulation here, as we know, that's a loaded term, and what I mean is something very specific, which is computing what I'll call the output probability of a random circuit. So the output probability is a quantity like this, which I'll call P0 of C. It's just the probability that when we apply the circuit, we measure, we get some particular fixed outcome, like all zeros. Okay? So that's the output probability. And so when I say that there's a worst to average case reduction that we proved for simulation, what we mean is not sampling from the output distribution, but computing an output probability. That's very, very important because a quantum computer does not natively compute an output probability. It samples from the output distribution. Is that clear? Any questions about that? Cool. But these are related questions, and one thing we've known for many years is to prove hardness of sampling, it suffices to prove hardness of computing an output probability to within a certain amount of additive error. And the additive error that's sort of the magic number for us turns out to be roughly 1 over the dimension of the Hilbert space. So it's like 1 over 2 to the n times a polynomial, or 2 to the minus n minus log n. And so that's what we want to achieve. If we could show that computing the output probability of a random circuit was hard to within that amount of additive error, we would prove hardness of sampling. Okay? So that is the goal. It turns out state-of-the-art hardness results don't do this. This is an open question. I think it's one of the most important open questions in quantum complexity. We can't do this, but we're getting closer, and we're sort of getting gradually closer every few years. So what they do is instead they prove hardness for computing an output probability to within some smaller additive error, which I'll call delta. Okay? So it's not 2 to the minus n minus log n. That's what we want. Instead, some smaller delta. And so proving hardness of that harder problem is a less impressive result. Okay. So let me tell you what's known. So just to get some notation, we're going to have n qubits to the circuit. And the size, the number of gates, is going to be m, which we're thinking of as n times d, where d is circuit depth. Okay? So, well, it's a timeline. Time is going here from my left to my right. In the first algorithm, delta was, we didn't even really talk about it. It was like 2 to the, we just said, oh, it's a polynomial in m. The first person to really quantify what delta was in these results was Ramis Movasag, who showed that for a very similar proof to ours, the delta that we could show was hard was 2 to the minus O of m cubed. Okay? Notice it's m here, the size, not n in the exponent. So that's an n times d cubed. 2 years later, we were able to improve this to 2 to the minus O of m log m, still the m in the exponent. And then, literally a few months ago, we were able to improve this to 2 to the minus n minus O of n to the epsilon for any constant epsilon. Okay? This is now the first time we were able to get an n rather than an m in the exponent, which is nice. But you can see we're still slightly short of what we would need to prove hardness of sampling. The difference is in this subleading term, n to the epsilon versus log. You can't make this up, but this is how it is. Any questions before I go on? Okay, great. So I want to give a proof sketch. So let me first talk about the exact case where we won't worry about delta. So here's how this works. Remember what the goal was. We're showing a worst to average case reduction. So the assumption is that there's a classical algorithm that compute the output probability of a random quantum circuit. We want to show how to use that to compute the output probability of our favorite circuit or our least favorite circuit, whatever it is, some fixed or worst case circuit. Right, so the first step, I think, is pretty clear. What we want to do is we want to take this worst-case circuit and we want to scramble it. We want to make it look more random. Right, we do this because, again, we assume we have the ability to compute the output probability of a random circuit. Right, so we want to make it look more random. How would I do this? Well, naively, it seems, I think, pretty clear. You'd sort of want to take C, the worst-case or fixed circuit that we want to know the output probability of. We would multiply each of its gates by something Haar random. Right, by the invariance property of the Haar measure, that will take a fixed 2-qubit gate, let's say, and map it to something completely random. Right? So this takes the worst case circuit and it makes it look completely random, but it doesn't quite work, and the reason is because no structure remains. The new circuit is sort of too scrambled. It's completely uncorrelated with the original circuit. Right? So what we're going to do, which I think is sort of interesting, is we give a way of sort of partially scrambling the worst case circuit. So I'll say that we sort of take the worst case circuit and construct a bunch of random but correlated circuits that I'll call C of theta, where theta is a real parameter between 0 and 1, with the property that when theta is really small, it's close to 0, C of theta is close to a random circuit. But when theta is 1, the circuit C of 1 is equal to the worst case circuit. Okay? This doesn't have to be so mysterious. One way to do this is just to take Ci, that's the ith gate of the worst case circuit, multiply it by Hi, your Haar random gate, and then multiply that by e to the minus I little hi theta, where little hi is the log of big Hi. Right? And the key point here is that if theta is 0, right, then this last part, drops out. It's the identity. And so that's completely random. It's Ci times Hi by the invariance of the Haar measure. But if theta is 1, right, of course we we inverted Hi, and then we're left with C, Ci, the worst case circuit. Right, so that we see this has the property that I'm talking about. Cool. So that's step 1. Step 2, we prove the existence of a real univariate polynomial, I'll call it Q of theta, of degree d. It happens to be that the degree is essentially the size of the circuit, the number of gates, with the property that Q of theta is equal to the output probability of C of theta. Okay? I'm not going to go into detail here. You can look at a variety of my talks on YouTube where I go into this in a lot of detail. But the main thing I want to say is that the proof is pretty much a straightforward consequence of the Feynman path integral on the computational basis. And that's pretty intuitive, right? If you think about if you expand the output probability of the random circuit in the Feynman path integral, what you're really doing is you're writing the output probability as a giant sum over an exponential number of paths, but the value of each path is the product of m gate entries. Right? And that's exactly what we're using here. Okay, so there's a polynomial. And then the next step is polynomial extrapolation. So what do? Well, we fix a bunch of small but distinct thetas, so theta 1, theta 2, through theta d plus 1, one more than the degree of the polynomial. Each one of these corresponds to a random but correlated circuit, right, by construction. And so because we're assuming we have the ability to compute the output probability of a random circuit, we can compute the output probability with high probability of all of these guys, right, which gives us d plus 1 points to a polynomial of degree d. Right? So at the end of the day, these evaluations completely specify the polynomial, and then we can recover the coefficients using polynomial extrapolation and then output q of 1, which gives us the output probability of our worst case circuit. I did that a little bit quickly, so any questions? Yeah.
You can compute Q of theta with like a small error. Is this like big extrapolation?
Yes, give me a second. That's exactly where this is going in like the next 30 seconds. Sorry, did you? Yeah, sure. Yes. Yeah, sure. So C of theta is the circuit in which you take all of the gates in the worst case circuit, that's the CIs, so like the ith gate in the worst case circuit is CI. You multiply it by a Haar random gate, HI, and then you multiply that by e to the minus I little hi theta. Now little hi is the log of big Hi, and the point is that if you have this discrepancy between theta equals 0 and theta equals 1. If theta equals 0, you get back a random circuit, Ci times Hi. If theta equals 1, you get back the worst case circuit because you cancel the Hi. Okay, cool. All right, cool. So that's how the proof works. But as was already mentioned, the really tricky thing is the robustness of this procedure to additive error. And remember, that's the really important open question, to show that this procedure is robust when these evaluations are faulty. They have some additive error. Okay. So let's just recast this problem in terms of a polynomial extrapolation problem. So it's just a problem about polynomials. Just makes it a little simpler to understand. Here's the problem. We know there's an ideal polynomial. I'll call that Q of theta. It's of degree d. Let's just make that a parameter. And the goal is to evaluate that polynomial at Q of 1. Okay, but we're not lucky enough to have at our fingertips the exact evaluation of that polynomial. Right? Instead, what we're given is, let's say, on the order of d squared, so we'll oversample a bit, faulty evaluation points like theta 1, y1, theta 2, y2, and so on. promise that most of these points are delta close to the evaluation of the polynomial. So most of these points, graphically, if you look at this, they're like these green points. They sort of delta hug the curve. Okay? But maybe a third of them are like these red points. They're like completely far away from the polynomial. Now, we don't know which is which, right? From the end user who's going to do this extrapolation process, all you know is that most of the points you're given are delta close, but some of the points are not delta close. They're very, very far, and you just know that most of them are close. You don't know which ones are close and which ones are not. Okay? Okay, cool. So we thought about this for a long time, about 2 years. And what we concluded is, given these points, it's probably a very, very hard problem to reconstruct exactly the polynomial Q. Okay? But in some sense, we don't need to do that. It turned out it's much easier not to reconstruct exactly Q, but to reconstruct a polynomial Q prime that delta agrees with some 2/3 of these points. Maybe not the same 2/3 as Q, but some 2/3, right? And so what our result from 2021 says, the main result of this paper is as follows. It says, let's consider any degree D polynomial, Q prime, that's delta close to 2/3 of these points. They may not be the same points as Q. They're different points, right? And so, for example, it could be like this blue curve, right? Q prime is this blue curve. Notice it's close to some of the same points, but it's not close to all the same points. And we don't even know which ones are close and which ones are not, so, right? Well, then what we say is, no matter what that polynomial is, all the way at 1, Q prime of 1 minus Q of 1 has to be upper bounded by little delta, that's the closeness of the good points, times big delta inverse to the D. Big delta inverse is the maximum theta parameter that we're using. Okay? And this result actually turns out to be tight in the sense that, for the regime that we care about, when big delta is like 1 over the polynomial degree, you can actually construct two sort of polynomials that have this sort of annoying feature where they're very close in this delta window, but then they're like, they saturate this bound. Okay? And you do that using Chebyshev polynomials. But anyway, this implies that, in terms of hardness, if we go back to the setting we described with circuits, that to compensate for this giant blow-up, this delta inverse to the D, we need to take little delta to be sufficiently small. So that's like 1 over D to the D. If I plug in D is equal to M, the size of the circuit, we get delta is 2 to the minus M log M, which was our hardness result. Okay? But the key point I want to say is that, to improve robustness, well, really you could hope to improve 2 parameters of this. Right? There's 2 ways that you could make this better. One thing is that you could imagine moving these points to be closer to the extrapolation point. Right? That's big delta. You could make big delta larger. Right? Your points are closer to your extrapolation point, you've made everything easier for yourself. Right? The second thing you could do, of course, is reduce the degree. Okay? And our focus is going to be on how to reduce the degree. I have to say, in 2021, we were rather pessimistic that we could do this. In particular because, where does the degree of the polynomial come from? It comes from this Feynman path integral, right? That's how we got the polynomial in the first place. And we didn't think there was going to be a clever solution to get over this. The polynomial was sort of not something that we had a lot of freedom in choosing, and so we thought, okay, the degree should be about M. Okay? And this is sort of where things stood, until about 6 months ago, in which we make progress by decreasing the polynomial degree. And this is sort of one of those proofs that, in retrospect, it seems almost obvious. Give me a second. In retrospect, it seems almost obvious. It is true that the technical details were tough to work out, and it's a long paper, but the idea is actually quite simple. Okay? Sorry, you had a question? Sure. Yes, exactly. So another thing you might do is you might use some property of this polynomials that, for example, separate you from Chebyshev polynomials. The extremal case, the case that sort of saturates this bound, right? Uh-huh. Okay. Oh, sure, if it's not adversarial, for example. Is that what you're saying? Yeah, okay, that too. But I don't like that so much. I think what that amounts to is assuming some sort of noise model or something. That's a little contrary to the spirit of quantum advantage, I think. It's just my opinion. So I want to think about these as adversarial errors. Now, what is true, the answer that you weren't saying, but I'll accept, is you might imagine that you find some property of these polynomials that came from the Feynman path integral, the special polynomials that you care about, that separates the polynomials from the extremal case of this, and you could do better, right? Like you could say, well, it's true that Chebyshev polynomials have this terrible behavior where they blow up, way out at 1, but at theta equal 1, but these are not Chebyshev polynomials, right? Nonetheless, I haven't really been able to do that except in what follows, where we are using something about this structure. So that's sort of the state of the art. So let me get back to it. So what we do is we improve the robustness of this argument by decreasing the polynomial degree. And in fact, the idea is pretty simple. So let me try to explain this. Here's the idea. Let's just consider this circuit. I'll call this Wn. W for worst case, but it's not a conventional worst case circuit. It has a special form. It acts on n qubits. And I want to think about this as sort of divided into two sub-circuits. So here I'm thinking about, time going from left to right, the inputs on the left and the outputs on the right. What I do is I cut the circuit in half, not in half, sorry, into WA and RB. Okay, so WA is going to consist of n to the epsilon qubits for any constant epsilon. Okay, that's the first n to the a qubits. And then RB is going to act on n minus n to the epsilon qubits. And we sort of cut the gates, between WA and RB. And if we ever have a gate that straddles the border between these two circuits, we're just going to make that the identity. Just going to throw it away and make it the identity. Okay? So that's W. Is it clear what I mean by WN? Not what I'm going to do with WN, but is it clear what I mean? Okay, cool. And RB, sorry, I should have said this. RB is just a random circuit. Right? So all of these gates are chosen randomly. Okay? Now, by construction, the output probability factorizes. Right? The probability, we've just cut all of the, the guys in between. So the output probability of the worst, of the Wn is the product of the output probability of WA and RB. Any questions? This is pretty straightforward, I think. No? Okay. Now, here's a fact. I think if you're a physicist, you're going to take this as a fact. As a computer scientist, it's very simple to see. That in fact, computing the output probability of just this top circuit, WA, is in fact already a hard problem. Right? And that's where we're using critically that the number of qubits that this circuit acts on is n to the epsilon. Right? It's essentially, polynomially smaller than the problem that we knew was hard, which was the output probability on the full circuit. Right? And, in computer science, a padding argument is the way we formalize it, but really polynomial factors don't usually matter. Okay? So in fact, computing the output probability of this WA is already a hard problem. Okay? But of course, it's not clear how to do that, because we don't have just WA, we also have RB. So that's going to be exactly the goal. We want to estimate the output probability of WA, and we know, just by algebra, by dividing both sides, we know that can be written as the output probability of Wn, that's the full circuit, divided by the output probability of RB. Right? Just divided, that's all that is. So the goal is going to be to get a multiplicative, like a constant, sufficiently small multiplicative estimate to WA, because that's the hard problem. Okay? And so to do that, we're going to require a multiplicative estimate of the numerator, the output probability of the full circuit, Wn, and the output probability of the random circuit, RB. Yeah? Okay, cool. So let's see, how do we do this? So like the RB is really easy, right? The RB is a random circuit. We're already assuming we have the ability to compute the output probability of a random circuit. Right, so we're going to do that. I'm just going to use an additional call to our algorithm in the sky that we're assuming works to compute the output probability. But the numerator is a little bit tricky. That's not random. And it's also not completely a worst case circuit. It's something in the sense of something we can argue about natively. It's some sort of weird thing that's sort of in between, right? Part of the circuit is random, that's RB, and then WA is arbitrary, right? Well, And this is where sort of the interesting work happens. So the idea is actually not so different from before. What we're going to do is use a worst to average case reduction, but where the worst case is going to be not an arbitrary circuit, an arbitrary worst case circuit like Shor's algorithm or whatever it is, but this circuit Wn. Okay? Now, but rather than in the prior argument where, if you remember what happened, we took each gate in the worst case circuit and we sort of perturbed it a little bit, right, by multiplying hi times e to the minus, little hi theta and so on. Instead of doing that, we're only going to extrapolate, we're only going to perturb by the circuits in WA, right? In RB, we're going to, just leave that the same. For all of the perturbed circuits, which we'll call Wn of theta, right, they're going to share the gates in that bottom part of the circuit, right? Or in other words, what are we doing? Remember what we did in the prior circuit? We had a worst case circuit. We wanted to compute the output probability, but we didn't know how to do that, right? So we parameterized, right? So we considered not C, but C of theta, right? In which we took each gate and we perturbed it a little bit, right? Now we're going to do the same thing, but we're only going to perturb the gates in this upper portion of the circuit. And we're going to keep all of the rest of the gates the same for all of the circuits, for every single Wn of theta. They're all going to share that same RB, right? In other words, what we're doing here is we're leaning into the fact that these circuits were correlated, and that wasn't a problem. We're correlating them even more, right? After all, before they were correlated because each circuit in the ensemble, each C of theta, shared the same random circuit hi, or random gate hi, and so on. Now they're going to share even more. They're also going to share this RB. But after all, that's random, right? So in some sense, that's what our algorithm is equipped to do. That's the idea. Now, the key is if you think about what the Feynman path integral does to this, right? And this is sort of the key point. Because we're only extrapolating on the gates of this top part of the circuit, right? This WA, the degree of this polynomial is now going to be the size of WA. Okay? So that's n to the epsilon, or O of n. It's not exactly n to the epsilon. It's n to the epsilon times whatever d you give it, right? And this is where the improvement comes in. Because now if you go to the previous slide, the blow up when we extrapolate the polynomial was like d to the d. Okay? And so what is the blow up? It's n to the epsilon to the n to the epsilon, which is just 2 to the 2 to the n to the epsilon log n to the epsilon. And that's where we get our hardness result. That's where we get the improvement. That's a little bit slick, so I'm happy to take questions before I go into something totally different. Yeah? That's a great question. Let me just be really clear, though. We didn't change what the sampling task is. Everything that I just described here is happening in the analysis. So, this is just telling you why you shouldn't expect to have a classical algorithm that does the same thing as the quantum circuit. At the end of the day, the quantum circuit, the experiment for the experimentalist doesn't change. So if you're an experimentalist, you can ignore all of this, right? The experimentalist just implements the random circuit on the all-zero state, measures all n qubits. That's it. That's all they're doing. This is saying why should there not exist a classical algorithm that does the same thing? Is that okay? You have a follow-up? Yeah, go ahead. Why can't I measure A and ignore B? But it's not clear why you would have any hardness, right? Because remember, measuring from the circuit is not the same. Like, that doesn't give you the ability to compute the output probability, right? I mean, it does to within like an additive error that's way larger, like a 1 over poly additive error, which is like it's a totally trivial for random circuits, right? Sorry, yeah, please. But please. Yeah, good. This is where a lot of the technical work comes in, which of course I'm very happily shoving under the rug. You have to sort of show that that doesn't really affect things, and there's sort of a clever embedding strategy. It's not very interesting, and it takes a lot of analysis, so I'm going to sort of ignore that for now. But it's a good question nonetheless. Any others? Yeah, please. You mean, can I solve the biggest problem that I've been working on for like 10 years? No, sadly not. And maybe I'll say, let's see, how much time? Yes, okay, yeah, good. So, sorry, how much? 5 minutes, okay, cool. I have 5 minutes and I wanted to say something about noise. So um, let me just say, I don't know how to go the other. Otherwise, obviously, I wouldn't be talking about it. I'd be like publishing it, you know. Okay, cool. So I did want to say a little bit about noise because that's the elephant in the room. So far, everything we've been talking about is why is exactly simulating a random circuit in principle hard. I think that's a very important question, but it's not the actual question that matters because of course these experiments are very noisy. A more realistic circuit might look something like this, where we have these ideal gates, these Cs, but then we also have these like ugly red dots that correspond to like single qubit noise channels, right? And we know that these experiments are ridiculously noisy, right? So for example, Google's original experiment reported something like 0.2% signal, 99.8% noise, right? This is like a noise machine. This is, by the way, a very impressive result, but it is a huge amount of noise. More recently, these experiments have gotten better. For example, Quantinuum's experiment was 35% signal, 65% noise. But if I'm a student, I get a 35% on a test. I'm still not happy about it, right? So I think the really interesting question is can classical simulation algorithms take advantage of uncorrected noise in RCS? And I think the first answer here, the sort of, the really obvious sort of intuitive answer is, well, it kind of depends highly on how we model noise. What do we mean by noise? In particular, I think there's sort of a fork in the road here, right? And the fork comes from the fact that everything we've been talking about so far has been in the asymptotic regime, right? Where we think about n, the number of qubits, as scaling, as growing larger, and we're asking, is there a polynomial in n time classical algorithm? Right? That's the same thing. But if we're thinking about scaling, then we also have to think about how does the error rate, the probability that each gate has an error, or each qubit or whatever has an error, how does that scale as a function of n, right? And so there's sort of two regimes. The one that we usually care about is a case in which this error rate is constant. It's constant of system size. So n is going to infinity, the error rate is staying the same, right? That's the standard setting in, for example, in fault tolerance. And here I'm just going to sort of stick my neck out and say that even though I don't know how to prove it in all cases, which in fact in some of the cases are very interesting, I sort of don't believe that there's going to be an exponential speed up here. Let's think about why that's happening. So the one thing I want to say is that this is not like the setting that we heard about earlier, like in Dorit's talk for fault tolerance, where you also, have the ability to like reset some qubits or, add fresh ancillas or whatever it is you want to do. This is the setting where you just have random gates, you have noise, you have random gates, you have noise, and that's it, right? And so, it seems a little bit ridiculous, sort of intuitively, that doing this, you can sort of keep going deeper and deeper and deeper, never correcting your noise, never resetting any qubits, and getting an advantage. And in fact, we've seen this. So this is, I think, this can be made rigorous by recent simulation algorithms. A very nice paper that Dorit, in fact, had in 2022, and my own paper about boson sampling and how to simulate that, and so on. But I think what's maybe more interesting is even in this regime where we're not correcting our errors, we don't have any resets, and we have a constant noise rate, as the system size is tending to infinity, there are still regimes in which we don't know how to prove they're easy, okay? And my favorite example of this is any time we have non-unital noise in the circuit, right? So the interesting thing there is, unlike in unital noise, unital noise is a generalization of depolarizing noise. Unital just means that the noise channel maps the identity to the identity, right? But one interesting fact about unital noise is it just increases entropy, right? So if you keep increasing entropy and increasing entropy, of course, eventually you're going to reach the maximally mixed state. For non-unital noise, that's not necessarily the case. Non-unital noise can reduce entropy in the system. And in fact, we have a paper recently where we can sort of formally show that you never, that the sort of the statistics of the output distribution of a circuit with non-unital noise completely different from that with unital noise. In particular, you never anti-concentrate. I don't have time to say what that means, but this is a statistical property that's needed for example, Dorit's algorithm to simulate the circuit. And so even in this case where we think it sort of should be easy, where the noise rate is constant, the system size going to infinity, if you have realistic noise, which should include some, say, depolarizing noise or unital noise and some non-unital noise, we don't know how to analyze that, okay? It's not that it's hard, it's just that we don't know how to say it's easy. The other hand, there's the low noise regime, in which the noise rate is actually decaying with the system size. This is not a realistic model particularly, but it does sort of capture what's going on from one experiment to a successive experiment, right? Like, for example, Google's 2021 experiment, 2023 experiment. The noise rate has to go down. Otherwise, their fidelities would not be good. And here we actually have hardness evidence, which ends up essentially reducing to the noiseless case. Right? So let me finish with one thought, which is just taking off my complexity theory hat for a moment. The really important question is which of these asymptotic settings, these theoretical models, is actually capturing the pragmatic difficulty of simulating the fixed system size Google circuit, right? 60-qubit circuit. And I think the answer here is we don't yet know. I think the true answer is that we're still learning about this. We need to think about this more. In particular, we need to invest a lot more time and effort into how classical algorithms can take advantage of realistic noise. Okay, that's a perfect place to end. Thanks a lot. Oh, okay.